Good morning, everybody. Welcome back. Today we are doing Unit 4, Topic 1 of the QCAA Chemistry syllabus, which is all about properties and structures of organic molecules. So we're talking all about organic molecules in this overview PowerPoint. So let's just get straight into it. The first thing you need to know about organic molecules is how they're named. So this is your basic IUPAC naming system. So the main thing you need to know first is the base. So is it an alkane, is it an alkene, or is it an alkyne? Really simple, easy way to tell them apart. If there's only single bonds between carbons in the main chain, it is an alkane. If that main chain has a double bond between two carbons, it'll be an alkene. If there's a triple bond between two carbons, it'll be an alkyne. So that is important. It is also important to note that a double bond between a carbon and an oxygen does not mean that it's an alkene. It's only between two carbons in the main chain. And we use the prefix to determine the start of that name. So the main chain name is, so if you count the number of carbons in the main chain, if you've got 7, then you're going to use the prefix for 7, which is hept in this case. So that's pretty easy. That's the prefixes. Using that information, you can then work out what the actual name of the main chain is, depending on if it's an alkane, alkene, or alkyne. So if it's 7 and it's only single bonds, it'll be heptane. If it is 7 but there's a double bond somewhere in there, it'd be heptene, and then triple bond heptyne. And of course you'd put somewhere in there a number to differentiate where that double or triple bond is. You also need to understand the difference between structural formulas extended and condensed. So the condensed structural formula has all the information in there, but it doesn't show any of the bonds. You have to work out the bonds yourself. The extended structural formula shows all of the bonds plus all of the atoms that are in there, carbons and hydrogens and anything else. And then this is just another example to show you how you might see it differently as well. So in this case, you've got an alcohol group, and so that's, I need my little pointer. So we've got an alcohol group coming off of here, and you can see it's just put on the end here. Whereas in this group, in this condensed structural formula here, the nitrogen is between the first carbon and the third, or the second carbon. So it's been put in that same spot here. Hopefully that makes sense. All right, functional groups, the ones that are specifically mentioned that you need to know: alkanes, alkenes, alkynes, alcohol groups, aldehydes, ketones, carboxylic acids, haloalkanes, so they're the things like fluoro, iodo, those sorts of things, bromo, esters, nitriles, amines, and amides. So you should be able to look at a formula with those structures in it and tell me what the structure is, what the prefix is, and what the suffix for that particular thing is. So we'll go quickly through the prefixes. So alkyl, alkenal, and alkynal. So this is the same as when you're doing a main chain. If you've got a functional group coming off of the main chain that has 3 carbons in it, then it will be a propyl. If it's got 3 carbons and one of them has a double bond, propenal. And if it's got 3 carbons and one of them has a triple bond, propynyl. So you just exact same as when you're doing a normal main chain naming, but you put it at the front of the name and you say ul instead of ane, iron, or whatever the other one is. Next, alcohol, the prefix is hydroxy. Aldehyde is a formal group. Ketone is oxo. Carboxylic acid is carboxy. The haloalkynes will just be whatever the halogen is, so bromo, fluoro, iodo. Esters are also called alkyl groups. Cyano is for nitriles, amino for amines, and amido for amides. And then you also need to know the suffixes. So we've got ane, ene, and ine we've already talked about. Alcohol is an ol group. Aldehyde is an al. Ketone is an one. Carboxylic acid is an oic acid. Haloalkanes don't have it because they're lower priority than even just the plain alkanes. Esters, it will be an O8. Nitriles, it will be nitrile. Amines will be amine, and amides will be amide. So those ones are pretty easy. And then this little picture here comes from compoundchem.com. It's a really great place for finding different posters and stuff like that. And it just shows you most of the different functional groups you can possibly get. There are also some that you definitely don't need to know. There's quite a few that you don't need to know, but some of the interesting ones are there. All of the ones that you do need to know should be on this little piece of paper. So if you don't know the structures of those, you need to be able to at least recognize it, if not draw it. So you might want to do some practice. All right. So that's all we're going to talk about in terms of actual organic structures. If you needed a little bit more help on the naming of them, then you need to go back to one of the other videos that have been done or look in your textbook or something like that. Now we're going to talk about structural isomers. So I like to think of isomers as same, but different. So there's lots of things that are the same about them, but there's something that's different. A structural isomer has the same molecular formula, so C5H12, but it has a different arrangement of atoms, so it's structurally different. So same, but different. In this case, pentane, C5H12, could also be isopentane, which you'll notice is a methyl butane group, or neopentane, which is a dimethyl propane group. So they have the same number of carbons, the same number of hydrogens, but they're structurally different. That is a structural isomer. Stereoisomer is a little bit different. They have the same structural formula, but have a different arrangement in space. So in this case, you will have heard hopefully of cis and trans. So this usually occurs around a double bond, possibly also a triple bond in some things. But the important thing to note is we are looking at the hydrogens and the continuation of the main chain. So in a cis molecule, the main chain continues on the same side as the main chain started. So it was on the left at the start, it continues and it's on the left at the end. So the hydrogens are also on the same side, so they continue on the right, or they start on the right and they end on the right. So this is a cis. The main chain starts on the same side and ends on the same side. In a trans, it's the opposite. So it starts on the left, it continues on the right, so it's swapped over. So cis means that it's on the same side, trans means that it's on the different side. So if it's asking you in a question to determine the structural isomer of something, you are finding something that is a different shape but has the same number of atoms. If they're asking you for the stereoisomer of something, then it is changing the way that you've got the main chain and the hydrogens around that double bond. Hopefully that made sense. All right, next, intermolecular forces. You should have been hearing about these things since the start of grade 11, if not sometime in grade 10. You should at this point know your intermolecular forces. There are 3. So the first one is just your basic dispersion forces. Everything has that. It is really, really weak, but it exists. Next, we have our dipole-dipole attractions. These are things that occur between molecules that are polar. So polar molecules have slight, very, very slight positive or negative charges, depending on where the electrons are hanging out in that bond. So we've got a slightly positive and a slightly negative, which means that the electrons are hanging more around here than they are here. Because of that, anything that's slightly positive is going to attract anything that's slightly negative, and that's going to give you your dipole-dipole attraction. Lastly, the strongest of the 3 intermolecular forces are hydrogen bonding. So it's very, very similar to the dipole-dipole attractions, but it occurs between hydrogen when hydrogen is bonded with some of the higher electronegative atoms like oxygen, fluorine, nitrogen, and chlorine. No, not chlorine. So the top 3. So the hydrogen bonding is the strongest of the 2 because the difference in electronegativity between these 2 molecules is high enough that the electrons spend the majority of their time right at this end. So this is going to be slightly more positive than these ones up here. That means it's going to be a slightly stronger bond and it's going to be harder to break. Hopefully that makes sense. Why do we need to know that? Why are you talking about that now? Because you need to be able to look at a molecule, particularly one of the organic molecules that you should be able to draw or name, and determine what the melting point, boiling point, and solubility, and I think also volatility of those molecules will be. You should be able to look at 2 of them and compare them and say which is going to have the strongest melting point or highest melting point and boiling point, and which one's going to have the highest solubility in water, those sorts of things. So the main thing that's important to know for that, if you understand this, you can understand the rest of it. The stronger the intermolecular force, the harder it is to break apart. So dispersion forces, super easy to break. Dipole-dipole, a little bit harder. And then hydrogen bonding, a little bit harder than that again. So the more hydrogen bonding you have, the harder it will be to break. So that's the first thing. The more polar a molecule it is, the more likely it is to be soluble in water. So if you have something like this, any sort of dipole-dipole or hydrogen bonding, that's more likely to be dissolved in water than something that just has dispersion forces. All right, so here is some broken down statements. The longer the chain, the higher the melting point and boiling point will be. So if you have a 1 carbon chain, it is going to have a much lower boiling point than an 8 carbon chain, which you can see in this picture here. So boiling point of methane, -164 versus octane, 128. So the longer the chain, the higher the melting and boiling point. Next, the more branched the chain, the lower the melting point and the boiling point. So a straight chain is going to be harder to break apart than a branched chain. And that's mainly to do with how closely it can fit together in a configuration. So something like pentane, that's just a flat chain there, you can picture that could just lay nice and easily on top of each other and get lots of dispersion forces between all of the individual molecules, making it harder to break apart. Whereas isopentane or neopentane, they're not going to fit together quite as nicely. There's not going to be as many intermolecular dispersion forces happening, so it's going to be easier to break them apart because there's less of those dispersion forces happening. And you can see that 36, 28, and 9.5. The last one, the stronger the intermolecular force, the higher the melting point and boiling point. We said that one before, but this is just to show you examples. So dipole-dipole here, we have an ether. So that has molecular weight, doesn't matter. They all have the same molecular weight. So it's 35 degrees for the boiling point of that. Same thing, the only difference is the placement of that oxygen is now at the end, and it has a hydrogen bond attached to it, and it's now got a boiling point of 117. So you can see that the hydrogen bonding has a much higher boiling point than the diethyl ether, even though the only real difference in the actual molecular structure is where that oxygen is, and the fact that this oxygen has a hydrogen attached to it. Hopefully that made sense. Again, this one's talking about solubility. So the longer the chain in an alcohol, the less soluble and volatile it becomes. So we're looking at alcohols because they have hydrogen bonding. So we know that there is a polar bond in there, but it's a similar concept. If it's not an alcohol, it could be a carboxylic acid, an aldehyde, a ketone, or a halide. So the longer the chain, the less soluble and volatile it becomes. The position of the alcohol can influence the solubility as well. So if we look at this big graph here, actually this one shows the solubility. The longer the chain, the less soluble it becomes. The next one, this shows the difference between the positions of the alcohol. So we start with ethanol, propanol, and propanol. So these two. This one here is propan-1-ol, and this one here is propan-2-ol. So you can see that this one's up here and this one's down here. So there is a difference between the position of those bonds. Again, we've got butanol here and buten-2-ol here. So the ones that are at the end, the primary alcohols, they are closer to this edge, whereas the other ones are closer to this edge. Hopefully that made sense. All right, reaction pathways. This is a big one. This one is going to catch you out. It's a hard thing to memorize, but it is something that you need to understand. So you can clearly see the specific characteristics that enable different molecules to undergo specific reactions based on the functional groups that are present. Things like acid-base reactions, oxidations can be used to help identify what class of organic compound that you have. So we'll talk quickly about the different reactions. The first one is a substitute reaction. So you are taking something and substituting it for something else. Usually it's a halogen is replacing a hydrogen or another halogen depending on what your molecule is. So in this case we've got methane. We're adding chlorine gas under conditions of heat and light, and we end up getting a what is this going to be? Chloromethane plus a hydrochloric acid. So you can see that we've replaced one of the hydrogens with the chlorine, and on this one we've replaced a chlorine with one of the hydrogens. In this case here, we are swapping an OH group for a bromine, so we're turning it into an alcohol and releasing a bromine molecule from the actual thing. So you're substituting one thing for another. Usually this occurs under specific conditions such as heat and light, or it's going to be a specific acidic or basic condition. And then a specific one that we're talking about down here, sodium hydroxide when added to a haloalkane like bromine or bromopropane will release the bromine and add the OH in its place, creating a propanol. So that's just this picture here. Addition reactions are mostly done on double bonds, can possibly be done on triple bonds as well. It specifically talks about this reaction here, which is when you add Br2 or bromine to an ethylene solution or any solution with a double bond. The bromine is going to break apart that double bond, and one bromine is going to attach to each end of that double bond that was broken. So you start with a double bonded molecule, you break apart that double bond, and then one thing is going to bond to each side of the double bond. Hopefully that made sense. So in this case here, this is one of the reactions that specifically is talked about in terms of identifying whether there is a double bond on a molecule. So if you add bromine, bromine is a brownish red color. But when it is in a molecule and not a Br2, it becomes colorless. So if you add bromine to a solution that contains double bond, it will go from a brownish red color to clear. So that's very important to understand. And then this one here is ethene and water, an addition reaction at high temperatures and pressures with a catalyst. So this one is phosphoric acid. You will turn ethene and water into ethanol. So that is one way to get ethanol. The other way is fermentation. But this way here, even though it's under high temperatures and pressures, it uses up all of its products to become its final product. It uses up all the reactants to become the final product. And again, there was a double bond here, but it broke and one hydrogen attached here and an OH attached there. Hopefully that makes sense. Carboxylic acids to esters. When combined with an alcohol under the right condition, carboxylic acids will react to become an ester. This is a reversible reaction, and the ester formed can undergo hydrolysis and become an alcohol and a carboxylic acid again. So carboxylic acid plus an alcohol of any sort will become an ester. So the R here, if you didn't already know, means the rest of the molecule. So the molecule plus the O will replace this OH group here and become the ester. The OH group plus the leftover H from the alcohol becomes a H2O. So that's an important one to understand. I know there was a question last year about esterification, so it's a good thing to remember. Carboxylic acids to amides, exact same reaction, but instead of using an alcohol, we're now using an amine, which is an NH2 group at the end. So it does the exact same thing. The H plus the OH combine to form water, and the amide is formed from the N group attaching where the O used to be. So exact same thing as with alcohol. It does require certain conditions, and it is called a condensation reaction as it produces water. Reduction reactions. Reduction reactions occur when a H is attached onto a molecule across a double or triple bond. It is similar to an addition reaction, however classified as reduction, as it involves the movement of electrons from hydrogen. So yeah, if you are adding an addition reaction with just hydrogen, it can also be recognized as a reduction reaction. This case here, even though this is some sort of lithium salt of some sort, I don't know what the name of that would be, lithium aluminium halide, something like that, I don't know. Two hydrogens attached to either end of this broken bond, which means that it's only reacting with hydrogen. So same with this one, we're using H2 to make an ethane. So we're calling that a reduction reaction. It's technically also addition, but anything that's just having hydrogens put on there, you can call reduction. Reaction pathway example using H and H2O. So we start as an alkane. We can do a reaction that's going to remove hydrogens and form, oh my goodness, words, and form a double bond. So that's an elimination reaction. So we're eliminating hydrogens and forming a double bond. From that, you can then add water under certain conditions and turn it into an alcohol group. You can then undergo another elimination reaction to get a ketone group, which you can then add water to again and do hydrolysis, which will get you 2 carboxylic acid groups. And then those can combine to form alkanes again. So this is a very complex pathway, but you should be able to look at what's happening and work out what type of reaction it is. So is it hydrolysis? Is it substitution? Is it elimination? Is it addition? If we go the backwards way, so start from here, from a ketone, we're adding H2, so this is our reduction reaction to get alcohol. From the alcohol, we're minusing the H2O, so that would be a condensation reaction. And then from the alkene to the alkane, we're adding H2, so that would also be a reduction reaction or an addition reaction. Does that make sense? I hope so. So I did mention elimination reactions, but I haven't talked about them yet. So an elimination reaction is when you are taking something away from the original molecule and replacing it with a double bond. So it's the opposite of an addition reaction. So in this case, we've got H and Br. We're taking away both of those to end up with KBr and water, and instead they're being replaced with a double bond in the center. And you can see the same thing with pentane and this one, pyridine. So that's essentially just explaining a little bit about what an elimination reaction is. These are the conditions in which they will work under, just in case you were interested in that. This is directly from the syllabus. This is the reaction pathways diagram that they have provided. So it is assumed that you will have a basic understanding of how the molecules move from one to another based on this diagram. I really hope that some of this makes sense. It's probably the most complex part of this particular syllabus is these reaction pathway things. And sometimes it's hard to remember, but you need to have a really solid grasp on what the structure of each of these different groups are and be able to take that structure and work out how do you change that to the other structure, what's happening when you change one to the other. If you don't know every single little particular, it's not the worst thing in the world. You might lose some points, but if you don't know how you can get from an alcohol to a ketone and you don't know the difference between the alcohol and the ketone, you're going to lose a lot of points. I hope that makes sense. All right, confirmatory tests. These are tests that can be done to work out, particularly if it's an alkane or an alkene, since most of the time those are colorless things. So this was the one we talked about before, bromine water. If you add bromine to an alkane, it will remain brown. If you add it to an alkene, it will go from brown to clear. This is a similar concept, but this confirmatory test, there's 2 of them, acidified potassium permanganate and acidified potassium dichromate. These react with tertiary alcohols. So tertiary alcohol being an alcohol that is attached to a carbon that's attached to 3 other carbons. Hopefully that makes sense. But both of these tests will not react and not have a color change when it is put in with a secondary or a primary alcohol, but will with a tertiary alcohol. So this one here, it goes, the normal color of it is this bluey green color, but a tertiary alcohol, it will not react. And this one is usually a purple color, so it will react with the tertiary, it will react with the primary and secondary, but not with the tertiary. Hopefully that makes sense. Yeah, hopefully that makes sense. All right, now moving on. Proteins. The protein structures contain the linear line of amino acids. Proteins. There are 4 different types of structures: primary, secondary, tertiary, or quaternary. The primary structure is just the linear amino acid sequence. Secondary structure, it does its first little bit of folding. So we've got, it goes into its secondary structure of alpha helixes or beta pleated sheets. Those then combine in the tertiary structure to fold around those things, and they make a bit of a folded structure that looks something like this. The quaternary structure is when one or more protein come together to form a protein complex. So primary, single line Secondary structure, alpha helixes or beta pleated sheets. Tertiary structure, folding around those and having molecular bonds between different sections of the protein. And quaternary structures, multiple proteins coming together. Enzymes are proteins that act as biological catalysts to speed up reactions. They work exactly the same as all sorts of catalysts that we use in chemistry, but they are the biological form of it. Each enzyme has a specific individual reaction that is based on its structure. It can break things up or build things down. No, break things down or build things up. So we start with a substrate, it attaches to the enzyme that works with it, and it can split it into two separate products. All right, monosaccharides we're talking about are sugars. They contain either an aldehyde or a ketone group and several alcohol groups. And they will have an empirical formula of CH2O. So the one most people know is glucose, C6H12O6. Fructose is, I think, C5H10O5. Galactose is, I don't know what galactose is. I think it's actually a 6-carbon chain as well, so it'd be C6H12O6. So that's, if you remember this, if you then can work out how many carbons it is, you just times the other ones by 5 as well, or 6 as well, whatever number that is. Disaccharides, a combination of two saccharides, monosaccharides coming together, and they have a glycosidic bond between the two. They are either alpha or beta glycosidic bonds. So a glycosidic linkage or a glycosidic bond, if it's alpha, it goes down between the two. If it's beta, it goes up between the two. That is essentially the big difference. It's about where on the first and fourth carbon the oxygen attaches, but that's essentially alpha goes down, beta goes up. All right, now this is a big slide, a very big slide, but this has been on a lot of the sample and mock exams that have been given. There's been a question to do with something related to this. So the main things that you'll talk about in terms of sugars or complex sugars are glucose, starch, and glycogen. So cellulose, did I just say glucose? Cellulose, starch, and glycogen. Cellulose is made up of beta glucoses. They are in a linear structure, they have no branches, and they compact together into a really solid structure that is very rigid and doesn't like to break apart. The starch can be in two forms, amylose and amylopectin. Both of them can be found in plants. Both are made of alpha glucoses, but amylose is a singular chain. It has no branching off of it, but it forms like a helix shape, and it is 1 to 4 alpha linkages. Amylopectin has linkages on the 1 to 4 carbons and the 1 and 6 carbons. So the 1 to 6 carbons is what forms the branches. So any molecule that has branches is going to have 1 to 4 alpha linkages because that's forming the branches. So the 1 to 4 linkages forms the straight chain. The 1 to 6 linkages gives you branches coming off of it. Amylopectin and glycogen are very similar. The difference being glycogen is an animal, amylopectin is in plants, and also the size. So glycogen is usually a branch every 10 subunits, whereas amylopectin is usually a branch every 20 subunits. Hopefully that makes sense. All right, moving on from the disaccharides, we've got triglycerides. So we're talking fatty acids. So they're usually made up of a glycerol molecule and 3 fatty acid chains. The fatty acid chains can all be the same or they can all be different. And the chains can also be saturated or unsaturated. So saturated being only has single bonds, whereas unsaturated you could have a double or a triple bond in there as well. The fatty acid chains do not need to be the same, and they can have different lengths and number of bonds. And saponification, this one is specifically mentioned, and I do know there was one question in one of the exams put out about saponification. So triglycerides can be used to form soap by adding sodium hydroxide or some sort of strong base. It is in a process called saponification. During this process, the cation from your strong acid, in this case sodium, forms an ionic bond with the ester molecule, and the OH attaches to the glycerol molecule to complete it after ester molecule breaks off. So we've got our glycerol molecule here. And this Na will attach itself to the glycerol molecule, the fatty acid chain. So the glycerol molecule will then get a H on the end to become glycerol. And then you'll end up with a crude soap, which is whatever the Na is attached to, which is in an ionic bond. Hopefully that makes a little bit of sense. So you break it apart, chop it off right here, and whatever is on this end is going to have the Na, and on this end is going to have the OH. Kind of hope that makes sense. How do soaps work? Kind of interesting. So you have your glycerol and you have your sodium hydroxide. As I said, the sodium attaches to the end of the fatty acids, and you end up with your glycerin molecule, which is your glycerol plus hydrogen and oxygen that's been attached to the end. For the actual soap, that's this stuff here. The fatty acid end is very hydrophobic. The sodium end is very hydrophilic. So the hydrophilic end, the sodium, attaches to, say, the water molecules that are around, whereas the hydrophobic end attaches to any lipids or dirt or anything like that and pulls it off with the water when the water washes away. So if you didn't actually have any water and you just put soap on your hands and didn't wash it off, it wouldn't really do anything. It would just attach itself to the dirt and lipids and not leave. The water is what kind of washes it away. And then polymers, the properties of polymers. So the degree of branching in a polymer has major implications on their properties. The less branching in the molecule there is, the higher the density and the stronger the polymer, which makes sense when you think about it. So something like high density polyethylene has very minor branching, maybe one molecule here or there. So it can sit a lot flatter against each other and becomes more dense. So the intermolecular bonds, particularly dispersion forces between them, there are a lot of dispersion forces happening in their area. There's not a lot of gaps, so there's more dispersion forces happening. Something like low density polyethylene, these long branches that are happening mean that it can't pack together nice and tightly. It can't fit really close together. So there's very small levels of intermolecular forces happening. So it's a lot easier to break them apart. They're a lot less strong. But that also means it's a lot more flexible. So the less branching in the molecule, the higher the density and the stronger the polymer. This gives it more rigidity and structure and enables it to resist higher temperatures. Sometimes you might not want rigidity and structure. You might want something that's flexible like a plastic bag, in which case you would definitely want to go with low density polyethylene instead of high density. So it's not saying that the more branching you have, the worse a polymer it is. Each type of polymer is going to have a specific situation that it's going to work best for. It does mention both of these, polypropylene and polystyrene, in the actual syllabus itself. It is talking about how the branches that come off of it, particularly in polypropylene, the propene group, the third group, and in polystyrene, the benzene group, how they sit in the molecule and how that has a big implication on its structure. So we have three ways that it can sit: syndiotactic, actactic, and isotactic. So actactic is a bit all over the place. It's irregular. The ups and downs don't have any sort of pattern. So that is atactic. Isotactic, all of the ups and downs are on the one side. So you can see it here. All of the benzene molecules are on the one side. And in this one, all of the methyl groups that are coming off are on the one side. So those things, isotactic. Iso meaning same. And then syndiotactic is highly regular. It's got a pattern. So up, down, up, down, down, up, down, up, down, up, down, up. So it has a very distinct pattern and is usually highly regular, making a crystalline structure. So syndiotactic, highly regular, repeating structure to alternating side, enables you to have high intermolecular forces and as such can bond to form highly crystalline structures. So these, if you had multiples of these, you can have another one of these would be here, and then there'd be bonding between those. So it allows for a lot of bonding between the different chains, which usually makes it a much stronger molecule. Atactic is irregular, so that it cannot easily pack together. There's low density, so it has weak intermolecular forces. Isotactic has all the functional groups appearing on the same side. This allows it to form linear strands that bond together but doesn't fully pack like syndiotactic. intermolecular forces are weaker than syneotactic but stronger than atactic. Forms a semi-crystalline structure. Hopefully that made a little bit of sense. I like to think about these iso meaning same side, syndio meaning it's like synchronized, it's a pattern, and then atactic is just all over the place. The last part of this is analytical techniques. So we've got firstly our protein analysis, which is chromatography. So chromatography can be used to separate proteins in order to apply further analytical techniques. That made sense. There are multiple ways to do these. This way is talking about separating them, including protein size, ionic strength, and charge of the protein. So this is size of the protein. So these little molecules work as little sieves that the different proteins can move through at different stages. So the smaller the protein, the more it's going to get stuck in all of the little beads, and it will take longer to get to the bottom because it's going to get stuck in all of them. Whereas the bigger proteins are going to take less time to get to the bottom because they're just going to move around them, and therefore are going to be able to move out quicker. You could also theoretically have the ionic charges, so the strength, so not theoretically, just you can actually have them, the strength of the thing. So beads have a positive charge. The more negative the particular molecule you have, the longer it's going to stay in there. The more positive it is, the quicker it's going to want to get out of there. So it'll move out in forms of the strength of the negative ion and the size of the negative ion as well. Electrophoresis separates proteins using electrical charge. The lower the weight, the lower weight particles will travel further than the higher weight sizes. This enables bands of proteins to form which can be extracted and tested further. So we have a negative electrode at the top, positive electrode at the bottom. So the negative particles are going to want to travel down to the bottom where the positive section is. The smaller it is, the easier it is, mainly because for each negative charge you have less weight that you have to pull down to the bottom. So the larger fragments are going to take a lot longer than the smaller fragments. Mass spectrometry. An electron is fired, or an electron beam is fired at molecules as they pass through it, and then based on their mass to charge ratio, they're going to be deflected because they go through a magnet, and they are reflected based on how heavy they are, and then they will hit the detector at different points, and you can then work out what the molecular weight is based on the mass to charge ratio. Hopefully that makes sense. The mass of the whole particle is typically the highest peak. This is however not true, as a minor peak can be represented as isotopes of the molecule and will therefore be m plus 1. So at the end here, the molecular mass of this one is 72. If you had a small peak here that was at say 73, that would be an isotope m plus 1, and your molecular weight would be 72. Again, this is another poster from compoundchem.com. Shows you that it goes through the electron beam, and then it goes through an electromagnet. The stronger it is, the bigger it is, the less deflected it will get, so it will hit the detector further out this way. If it's lighter, then it will be deflected more, so it will hit further out this way. And then these are some common things you'll find. So CH3 group is at 15, C2H5 is at 29, so on and so forth. And then we've got Xray crystallography. So an X-ray beam is shined to a crystallized molecule. When the X-ray beam is turned on, the X-rays will hit the crystal and a pattern of spots is made on the screen at the other side. The pattern shows where the X-rays hit particles inside the crystals. This is called a diffraction pattern. Some spots are darker than others. Very complicated mathematics called Fourier transformations is done using a computer to change the spot pattern into a picture showing how the particles are arranged. So that is very complex. You definitely won't need to work out what the structure of something is based on these diffraction patterns, but you may need to have a basic understanding of what X-ray crystallography is. Alright, lucky last is infrared spectroscopy. This is an analysis of infrared light interacting with the molecule. So the main use of this technique is in organic and inorganic chemistry. It is used by chemists to determine functional groups in molecules. The IR spectroscopy, which is this thing down the bottom, measures the vibrations of the atoms, and based on this, it is possible to determine the functional groups. So you use your where the peak is, and in your formula book there is a table that will say, okay, a peak that is found at 1,450 to 1,350 is an alkane bend. So it will tell you if you have a peak at 2,800 to 3,000, it's a carboxylic acid. So you just need to be able to recognize, well, what actually does that mean? This is a very good diagram that shows you like exactly it's a stretch or it's a bend, and where exactly it fits and how they overlap. So some things say at 1,200 it could be an alphylatic amine, an haloalkene, or an ester ether alcohol or carboxylic acid. So it could be any of those. So you can use the combination of the different peaks or this in combination with one of the other techniques to determine what your molecule actually is. I hope some of that helped. A lot of it, this again is just a brief overview of everything. You should have a good understanding of most of these things by now. And if you're looking at something and you're really confused, you probably need to do a bit of further study on it. But anyway, that's the end of Unit 4, Topic 1. I hope you found this useful, and I shall see you in the next one, which is Unit 4, Topic 2.